Everybody, happy Friday and welcome to another segment of Echo Live, coming to you through Zoom and through the Michigan Science Center's Facebook page. Thank you for joining us today. We'll be talking about physics, and more specifically, we'll be talking about Newton's first law. Before we get started, since we'll be relying on the chat feature, either in Zoom or through Facebook, go ahead and tell me in the chat, tell us that you're here, tell us that you're watching, and you can tell us your name, what city you're watching from, or even what grade you're in, if you think that would be helpful. So tell us that you're here. We're so happy that we have so many familiar faces and familiar friends joining us for Facebook Live, and even some new ones. Now, today we'll be talking about one of Newton's laws. Now, Newton was a very important physicist a very long time ago, but even though Newton did work on physics hundreds of years ago, his laws are still extremely important to physicists today. We'll be talking about Newton's first law, which is also known as the law of inertia. Now, inertia can be kind of a tricky topic, but we do have some very easy ways to show that inertia is all around us. It's a force that we are experiencing all the time. Let's first start just by talking about what inertia is. So if we were to read the definition of inertia, it says, which it is also referred to as the law of inertia, or Newton's first law. It states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction unless it's acted on by an outside force. This is a big chunk of words, but we're going to break it down into its pieces. The one way you can think about this is that if you've ever been driving in a car and the car slowly comes to a stop, your body will slowly come to a stop with the car. However, if you're driving in a car and the car has to stop very quickly, your body will actually keep moving. That's actually why seatbelts are so important, because if your car came to a stop, your body wants to remain in motion. That's that second part of Newton's first law. An object in motion will stay in motion. So unless your seatbelt was the outside force, your body would want to remain in motion. Thankfully, your seatbelt is there to stop that force of inertia, keep you in your seat, and keep you nice and safe. So inertia is around us all the time. And I have some fun demonstrations here in the studio that I can show how inertia works. The first one we'll talk about is using these bead garlands here. Now, this is a cup full of bead garland. I've just tied the end of it here to a rubber band so that I don't lose it here inside this cup. But this is about 200 feet of bead garland right here, just coiled up inside the cup. Now, how the beads are right now is actually a very good example of Newton's first law. These beads are at rest, and they'll stay at rest unless an outside force were to act on them. Now, it's pretty easy for me to become that outside force, right? I could very easily just lift up on the beads, giving them enough motion or giving them enough energy to overcome their inertia and causing them to be in motion. Now, if I want them to go back at rest or go back to being at rest, right, just set them back down and they go back to that state of rest. So I can be that outside force. But there's also another force that's acting on these beads that are sitting in this cup that's invisible, something that we're not always thinking about, but is always there. It's the same force that keeps our 2 feet on the ground and keeps all of our stuff from floating away out into outer space. That force is gravity. So gravity is also holding these beads down inside the cup. When I move the beads, right, I can give them different amounts of energy, especially potential or stored energy. So if I pick the beads up way up high, I can give them more stored energy. The higher I lift them, the more their potential is for converting back into that energy of motion. Just like when you reach the top of a roller coaster, at that exact moment before you fly down the hill, right, you have the most potential energy because you've reached your highest point. Same thing would happen with these beads. So I've actually just set them here on this container, and we're going to actually watch the force of gravity overcome the force of inertia that's keeping these beads at rest. So we'll zoom out just a little, and we're going to watch what happens when I give these beads just a little bit of a tug. And this time, instead of dropping them back down into the cup, I'm actually just going to let the beads fall forward over the edge of the table and watch what happens. We've seen that that force of gravity acting even on just those first few beads was enough to pull all of the beads out of the cup to overcome their original inertia that kept them here sitting at rest. Now, another really fun way to talk about the force of inertia is actually using a classic magic trick. You ever heard of the tablecloth trick? Magicians and other people do this trick all the time where you can actually yank a tablecloth off the table, leaving all of the objects that were set at the table exactly in their place, leaving them completely undisturbed, nothing broken, nothing toppled over. And so we're actually going to be teaching you how to use this force of inertia, or how to manipulate this force of inertia, so that you can try this trick yourself. We'll start with a small version of this experiment using just a piece of paper and a somewhat heavy object. So if we want our object to stay at rest, right, we need that force of inertia to be greater than the force that's acting on the system. So we've chosen a piece of paper for this demonstration because it doesn't have any seams around the outside. So you want to choose a nice flat piece of paper. You can start by keeping your piece of paper pretty close to the edge of the table. Let's zoom down here. And what I'm going to do, maybe it would be helpful if I turned off my virtual background. But what we're going to be doing is pulling on the piece of paper and seeing if we can leave this bottle of isopropyl alcohol completely in its place and undisturbed. So let's go ahead, and first I'll be just pulling straight back on the paper, and let's see what happens. 1, 2, 3. Now you'll notice that wasn't perfect. The bottle is still sitting on the table, pretty much undisturbed, but we did see some motion. We did see that the bottle moved. And that has a lot to do with the direction of the force that I put on this paper. One thing that people often mess up while they're trying this tablecloth trick is actually by lifting up or by lifting back on the tablecloth. What you actually want to do when you're attempting this trick is you want to pull down on the paper or on your tablecloth. This will prevent any air from getting underneath the piece of paper, which could cause your bottle to move, right? And if we give this bottle any motion, Newton's first law says that it will want to stay in motion. So we want to reduce the amount of forces that cause this bottle to move at all. And one way we can do that is actually by pulling straight down on the paper. So let's give that another shot. We'll scoot it just closer to the edge, and this time we're pulling straight down in 3, 2, 1. And you'll notice that time we had very little movement at all. Another way that you can reduce the amount of force you put on your objects is by choosing something that doesn't create a lot of friction. This black tablecloth is actually really great for this experiment because it's nice and smooth. Fabrics that are made of things like felt or have a lot of fibers in them aren't great for the tablecloth trick because having that kind of soft surface will create some friction, which could create some traction and move some of your objects as you try this experiment. This tablecloth is pretty great for this experiment. So I'm going to scoot a couple objects out of the way, and we're going to try doing this again, but just a little bit bigger. So this time we'll actually be pulling our tablecloth with these objects on it, which we've used earlier in the week for some Echo Live programming. And we're going to do the exact same thing. Now, you'll notice that this is just a cut piece of fabric. And so you can even see that there are some strings starting to fray away because there's no hem. So if you don't have a tablecloth at home that has no hem, you can try a plastic tablecloth or try cutting a piece of fabric that has no hem. So there's no kind of sewn edge on this, which could kind of bump our objects or cause them to start to move around as we yank the tablecloth out. So let's try this again. I'm going to stand just over here to the side. And remember that when we do this experiment, we're pulling down on the tablecloth, not back towards your body, to prevent that movement of air underneath. All right, so here we go in 3, 2, 1. And you can see that our objects have barely moved at all. It's amazing. This is an experiment that you can and you should try at home to practice manipulating inertia. I'll set this activity back up one more time. And something else fun you can try is by moving around your objects. Now you'll notice that the objects I chose for all of my tablecloth tricks, none of them are breakable. I've got plastic containers I've got containers that have a little bit of weight to them as well. So this trick works best when you have some mass inside your objects on the table. If your objects are too light, right, that force of gravity is acting on them less. Gravity is actually stronger on objects with more mass or more weight. And so you want to choose objects that have a little bit of weight to them, not too heavy that the tablecloth can't get out from under them. But each of these containers of, my baking soda, my salt, and my water are about half full, giving them a little bit of mass. We can also rearrange these objects. So instead of spreading them all out, I'm actually going to try stacking them on the table. So this is another experiment that you can and should try. Again, they're all made of plastic, so even if they do fall, nothing's going to break. I don't have a huge mess to clean up. Always best to practice with things that are safe until you've mastered the trick, and then you can move on to some things that are maybe a little bit more tricky. So let's do this trick one more time. Again, pulling straight down on our tablecloth in 3, 2, 1. And we've had a little bit of movement here. One thing to think about is if we've stacked a heavy object on top, that object could cause your tower to topple over. So you always want to stack your objects from most heavy at the bottom to least heavy at the top, because this one on the bottom is the one that we want to really focus on keeping its inertia at rest, or keeping its motion at rest, thanks to that power of inertia. So now is a great time to pause for any questions. I know we've talked a good deal about inertia so far. I do have one last demonstration to talk about with you, but now is a great time to pause for any questions you have about our tablecloth trick, about our inertia beads, or about this concept of Newton's first law. So if you do have questions, go ahead and type them in the chat. We're also going to take this time to, of course, thank our sponsors like the DTE Energy Foundation. These programs are brought to you free every single weekday at 2:30 p.m. Eastern, thanks to the sponsors that are keeping the Science Center going even while we are closed to the public. So if you are enjoying Echo Live, as always, make sure you are sharing these programs on your Facebook page or with anyone else you know who might be interested in joining a live program or watching them on our Facebook page after they are posted. So let's see if we do have any questions in our chat before we move on to our last demonstration. How does air not go under the stuff? That is a great question. That's the reason that we're pulling straight down on the tablecloth. If you do lift up, you do allow that air to travel through the tablecloth or under the tablecloth, which could cause your objects to topple. If you pull straight down, there's really no opening for that air to get up and under the tablecloth. And so it's really important to this trick that the direction of the force you put on the tablecloth is straight down. What is Newton's second law? Newton's second law has a lot to do with the rockets that we talked about, which says that for every action, there is an equal and opposite reaction. But we'll get to more of Newton's laws over some different Echo Live programs. Why do you need mass for this project? This is something that you should experiment with at home. So maybe start with some empty containers, some very lightweight containers, and you'll actually get to see how important having this mass is. Having mass increases the amount of gravitational pull is pulling on this object in total. So the heavier the object, the more it will want to stay in its exact place, which means you need a greater force to overcome that inertia. Do you ever get nervous when you do this? I'll be honest and say yes, that I've always wanted to try this one live. I can be kind of nervous because if it doesn't work, it can be a little bit embarrassing, but I'm very thankful that it worked today. But I'm not nervous anything's gonna break since I did choose objects that I'm not so worried about hitting the ground. So that's always good too. Would it work with something really heavy? Not really, not as easily. So if your object is really heavy, it's going to kind of make it more difficult to move that tablecloth underneath it. So I did try using a bigger bucket, one of those 5-gallon buckets that I've been using throughout this program. I did try using that with about maybe 6 inches of water in the bottom, but that was extremely heavy. And so it did immediately move with the tablecloth. Thankfully, it didn't spill. I caught it before it did, but didn't work so great for this experiment. But maybe that's a variable that you could manipulate, is what would you need to change in order to do this same trick with a very heavy object? I see some suggestions for future Echo programs, and I love that. So let's see. Elnora Marie says that her son would love us to make a catapult. And so I would definitely love to do a segment on simple machines if that's something that you are interested in at home. So if you do have suggestions, please type them in the chat or send them to us over Facebook message. Make sure you're sending them to the Michigan Science Center. We want to bring you programming that you find interesting, that you think is fun, and maybe trying to cover some of that content that you are learning in school or were learning in school. We want to be that resource for you, so definitely feel free to let us know. Now, we'll talk about one last concept that has to do with inertia before we go on to our final demonstration. So the concept we'll be talking about is how this concept of inertia ties into things that are rotating. So anything that is rotating or spinning around has something that we call angular momentum. The easiest way to think about this force is actually by thinking about a figure skater. So I'm sure we've all seen a figure skater either on TV or in real life spinning around on the ice. And you'll notice that there's kind of an interesting effect that happens when a figure skater pulls their arms in close to their body. I have a clip of this so that we can see it happening in slow motion. Let's see if it starts to work. There we go. So we've got our figure skater starting to spin around. And this will play over and over so we can break it down. You'll see that as her arms move into her body, overall, she begins to spin much more quickly. Angular momentum is another of those forces in physics, but it's basically a product of your moment of inertia, which we've talked about now, combined with your speed. Now, angular momentum wants to maintain a constant level. And so your angular momentum is constant. That means that if you change your inertia, there has to be a change in velocity that goes with it. So if you decrease your moment of inertia, which is actually what's happening to our figure skater here when she pulls her arms in, as she decreases her moment of inertia, her velocity has to increase. So a decrease in one variable will result in an increase in the other variable to compensate. So this happens to figure skaters, but figure skaters and people are definitely not the only things that are subject to angular momentum. It really applies to anything that's spinning. There are some forms of extreme weather here on Earth and in outer space that take place based on this angular momentum. Can you think of any extreme weather that rely on rotational energy or this angular momentum in order to fuel their power? So tell me in the chat, what kind of extreme weather might I be thinking of that has rotational energy? No guesses yet, but let's see. A tornado? Oh, great. We've got some great guesses rolling in. Tornadoes are definitely spinning. Hurricanes as well. Tornadoes, hurricanes, even things like whirlpools, right? All these forms of extreme weather rely on that angular momentum, that rotational energy in order to kind of fuel their destructive power. It'd be no fun at all if we didn't end Echo Live this week with a do not try this at home demonstration. But we can actually create something that we call a fire tornado right here inside the studio. So we'll be using these same principles of inertia and angular momentum that we've talked about so far. We need a few pieces of equipment in order to create a fire tornado. The first thing is we'll need a source of a flame. So I do have our source of our flame right here. So we're actually going to set this right here on the table. I've got kind of a baking sheet here to keep the hot dish that we're going to be creating our fire in off the table, so we are being safe. We're not going to have anything melting. We'll be using our isopropyl alcohol as our fuel. So if you remember back to our lesson on kaboomistry, we talked about the fire triangle. So we have a fuel source, an ignition source, and there's oxygen in the air all around us. This is also a great time to mention that we're, of course, going to be safe while we're doing this fire tornado demonstration. This is not something you should ever try at home because it can be extremely dangerous. Fire is definitely something that you should never play with. So we do have a fire extinguisher here also. I'm hoping to not have to use it, but as always, we're always prepared just in case something does happen. So we are prepared. I'll put my safety goggles on right now, and I won't take them off. Now, when I do ignite our flame, I'll put on my safety gloves here, but first we'll just kind of soak the cotton balls inside this dish with some isopropyl alcohol. And we'll kind of let those kind of soak for just a moment there. Now, since this fire tornado will happen pretty quickly once it gets started, we'll just give you a brief rundown of how this relates to angular momentum. Now, we'll be taking our flame here and we'll actually be enclosing it in a big container or a big column made of acrylic. The column I have right here, but you'll notice that I cut, or I left 2 cuts in the side so that we can still have air or oxygen entering this column. That's actually what's going to create that rotational energy. So as our flame causes the air inside to warm up, it'll actually start to rise, which is going to pull some air through the sides of our walls, causing that first initial angular momentum. So let's go ahead and we'll start with just that part here. So we'll go ahead and I will put on my safety gloves. My hair is tied back, my goggles are on, and let's go ahead and we'll just light our fuel source, or we'll light our combustion reaction here. Now we'll place our outer walls around our fire tornado, creating that angular momentum. Now, the next piece that we'll be adding is a roof or a chimney. So what we'll be adding is just this small radius, if you think back to our figure skater, for our air to travel out of. Just like with our figure skater, when we decrease the size of the opening that air has to travel out of, the speed of the tornado will increase. So we've got it slowly starting to spin around the edges. And then lastly, we'll be adding this tall chimney, the final piece of our fire tornado, in order to further decrease that moment of inertia and increase the velocity of this reaction. And we can see that we've now really picked up the speed of our tornado here. That air is moving very quickly up out the narrower opening. But if we want to slow this back down, right, all we have to do is create a change in the moment of inertia. If we take away our column, our velocity will start to decrease. If we then take off the roof and really remove that small opening that the flame has been forced to go out of, right, we even further decrease that moment of inertia, or we increase the moment of inertia, and we'll decrease the velocity of the flame. Now, there's a lot of hot air, and this air wants to kind of continue, just like we've talked about. An object at rest will stay at rest, an object in motion will stay in motion. So really, until we kind of remove all of the outer walls, we're going to keep having this kind of rotational energy take place. So we'll kind of, I'm going to step this way to make sure I have space to set this down. We watch our reaction completely fizzle out. And then we'll actually just snuff it by removing the oxygen from this reaction. So just like you would snuff a candle, if we place this container over the top, and we'll leave it because that's nice and warm. But since we've removed the oxygen from our reaction, we still got fire there. We'll keep that there. Always good to be extra, extra safe until we are sure that fire has gone out. So this is it for Echo Live this week. We're bringing these programs to you every weekday at 2:30 p.m. Eastern. We hope you are enjoying these lessons. Again, we want to know from you, what would you like us to talk about next? We've got a full week of programs planned next week, every day at 2:30 p.m. So thank you guys so much for joining. This has been so much fun, and I will see you on Monday at 2:30. Have a great weekend.